Hello students, welcome to this lecture series on the subject of advanced semiconductor devices, subject code KEC 056. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. This is our first lecture today in this series. So, I am going to give you an introduction to the significance of semiconductor devices. Okay. So, let us start. Since the mid 20th century, the electronics industry has enjoyed phenomenal growth and is now the largest industry in the world. The foundation of the electronics industry, the so called gadgets which we use these days, at the heart of these gadgets or electronic devices is some kind of a semiconductor device. In fact, all the electronic devices are also known as semiconductor devices also. To meet the tremendous demand of this industry, the semiconductor devices have also evolved rapidly. The structure, the architecture, the way they are connected or the way they are manufactured or designed, these aspects of any semiconductor device has seen significant improvement over the past many years. Now, you can have a metal, you can use metals for a lot of conductivity, you can use insulators for providing insulation between different conducting regions, but it is actually the semiconductor which is used widely for electronic devices. The simple reason being that a semiconductor device is so flexible that it can be tuned for high conductivity like a metal. It can also be connected or designed in such a way that it works like an insulator also. So, this tuning capability of a semiconductor device is what makes it so useful. The aim of today's lecture is to understand the bigger picture and the sort of a background where these semiconductor devices and their significance is coming from. Okay. So, I want to show you these two images today. If you see the image on the left, you would see a large room with a lot of wires and pieces of equipments connected together and two people busy in recording some data. And if you see the image on the right, it shows you a sort of a chip or an IC which is comparable to the size of a fingertip. Okay. And the amazing thing is that both the images on the left and the right, they are basically doing the same thing. Okay. So, the image on the left is also a processor trying to record some information. The IC shown on the right is also a processor. And if we compare these two, we would see that one requires a lot of area, space, cooling capabilities, manpower is being needed, but on the processor on the right is free from these kind of requirements. An interesting fact is that the amount of storage and switching capability of the fingertip processor is far superior to this processor which is on the left hand side. Okay. So, we have actually travelled this type of a distance, this much distance only by using advancements or implementing advancements in semiconductor devices. Okay. Another image I want to show you, the image on the left is a very iconic image known as world's first phone call being done by Alexander Graham Bell to his assistant Dr. Watson, and you can see that there is a separate mouthpiece, earpiece, lot of wires connected together and the excitement of people around it. From here we have travelled somewhere here, okay, and we have managed to reach somewhere here. And in today's world we use our so called phone is being used not only for communication, but a host of other activities also. So, the entire processor has actually come in your hand where you can do a multiple activities using a single gadget. Okay. How we have managed to reach here? The answer lies in the advancement or development of a semiconductor device, and when we say semiconductor device, we are referring to what is known as the transistor, and when we say transistor, we are referring to a MOSFET. All of you may be familiar with the MOSFET, metal oxide semiconductor field effect transistor, which is basically the building block of every electronic device and by itself is a semiconducting device. Okay. The graph on the left, the vertical axis of this graph tells you about the transistor density in millions per unit area. Okay. So, millions of transistor per square mm. So, how many transistors you can fabricate per unit area across a 1 mm by 1 mm silicon substrate, how many transistors you can manufacture or fabricate, that over the years has gone up significantly. In fact, we have exceeded 1 trillion transistors per unit area already. Okay. How we have done? For this, the benchmark has been the world famous Moore's law. What Moore's law says, that every 18 months the number of transistors per unit area on a silicon chip is going to double, and the industry has actually adopted it as a challenge or a benchmark, that they now actually try to follow Moore's law for past many decades. Okay. So, that Moore's law becomes a benchmark as a driving force for industry, and the major industrial players, they do what? They try to double the number of transistors every 18 months or so. When you double the number of transistors, the way to do it is to reduce the dimensions, the so called downscaling of dimensions. Okay. So, the graph on the right tells you the transistor gate pitch, which has reduced over the past many years. So, you reduce the dimensions by downscaling, and you cram more of these components in the same area, so that your functionality increases, okay. Your capability, your switching capability, processing power of your devices start to increase, and you are able to provide more functionality, and you are also able to make your devices more compact. Okay. And the heart of this trend is the so called transistor, which is a semiconductor device. And the objective of to study this course is to study the working of advanced semiconductor devices, which actually make these industrial trends happen. Okay. So, now let us proceed towards the actual content of this subject. There is a sort of a hierarchy to any semiconductor device or an integrated circuit. If you take any IC in hand, you can consider it as a system. Now, try to dive deep into this system. You would see certain modules connected together, where each module is a system in itself. If you dive into the module, you would see some kind of a logic being implemented. Okay. Inside this logic, you would see transistors connected in a circuit. If you dive into a transistor, you would see regions like gate, source, drain, substrate. Okay. And inside this material is what is a single crystal or a purely crystalline material, usually silicon, okay, which is the most widely used semiconducting material. So, if we try to analyze from the material level or the material point of view, you would see the crystal structure of a semiconductor. A crystal is nothing but a region or a material which is characterized by a well structured periodic placement of atoms. If you sit at the position of an atom and look around, you would see the same 3-dimensional arrangement even if you change your position. Such is the level of periodicity in a crystal. The smallest assembly of atoms that can be repeated to form the entire crystal is what is known as a primitive cell, okay, which has a certain dimension, and that dimension is a lattice constant. Okay. So, the images shown on your screen fall in the category of a cubic crystal structure. So, you can have a simple cubic structure, okay, where each face or where each corner of the cube has a single atom. Okay. You can have a body centered cubic arrangement, where in addition to these edge atoms, you can also have an additional atom at the center of this body. You can have a face centered cubic structure, where in addition to these edge atoms, you can have one atom at each face of the cube. Now, what it is basically telling you, how different atoms can be placed together to form a crystal, and each crystal is characterized by its periodicity. So, if you analyze a small repeating unit, the primitive unit cell, you can estimate the material or say eventually the electrical properties of that material. Okay. So, the aim of studying the crystal structure is to focus on this periodicity. Okay. In 3 dimensions, there are basically 14 different arrangements in which atoms can be arranged inside a crystal. These are very widely known as Bravais lattices. Okay. Within these 14 arrangements, they can be further classified into 7 symmetric configuration depending upon the crystal geometry and where the atoms are located. The symmetry of Bravais lattice results in same neighboring environment for every lattice point where an atom may be present. Okay. Again I am going to stress upon the periodic nature of this crystal. This periodicity has a major impact on the conductivity of this material. Okay. And depending upon how atoms are arranged or how they where they are located, that is going to decide in a single unit cell how many atoms are packed together. If there are lot of atoms, the so called packing density is very high. If there are lot of atoms packed together in a small area, you are going to have lot of electrons, valence electrons also packed around, and that is going to eventually end up with higher conductivity. So, that is the basic objective of studying the crystal structure. Let us try to relate this crystal structure to the actual semiconductors. Many important semiconductors which are widely used, they either have the diamond or a zinc blende lattice structures. This belong to the tetrahedral category of your Bravais lattices. That is, each atom is surrounded by 4 equidistant nearest neighbors, just like a tetrahedron, and that atom itself lies at the corner of this tetrahedron. Okay. The bond between 2 nearest neighbors is formed by 2 electrons with opposite spins. Okay. The diamond and the zinc blende lattices can be considered as 2 interpenetrating face centered cubic lattices or FCC lattice, and we have seen what is an FCC lattice. So, in that single cube cell, single unit cell, at every corner of this cube you are going to have one atom, and each cube has 6 faces. So, at the center of each face you are going to have 6 additional atoms also. Okay. So, for the diamond lattice structure such as silicon, germanium, your most widely used semiconductors actually have a diamond lattice structure, okay, where all the atoms are the same, whereas in a zinc blende lattice you would have some kind of an alloy arrangement or a compound arrangement where you have 2 different elements. Now, if you try to basically differentiate between different semiconductors itself, the so called material which have conductivity between a metal and an insulator, you can have either elemental semiconductors, your most probably the group 4 elements like silicon, germanium, or you can have compound semiconductors, say group 3 and group 5 elements coming together and forming one semiconducting material, okay, like gallium and arsenic forming an alloy together called gallium arsenide. So, from the crystal point of view, one sublattice structure is of gallium and another sublattice structure is that of an arsenic. So, the lattice arrangement on the left, the tetrahedron structure is that of a diamond lattice structure, okay, like silicon, germanium, carbon, okay. Or you can have the zinc blende structure for so called compound semiconductors, where you have the tetrahedron arrangement also in a small sublattice structure, one for gallium, another for arsenic. Okay. So, this crystal structure, due to its periodicity and packing fraction, it is going to eventually have a major impact on the electrical characteristics or the conductivity level of the device in which this material is being used. Okay. Since semiconductor devices are built on or near the surface, okay, so all the action basically takes place on the surface only. The so called channel of a MOSFET is so thin that the bulk properties do not have major impact, only the surface tends to play a lot of role. The orientation and properties of the surface crystal planes are also important now. A convenient method of defining the various planes in a crystal is to use what is known as Miller indices. These indices are determined by the first finding the intercepts of the plane with the 3 basis axes in terms of the lattice constants or the primitive cells. Okay. And then this is followed by taking the reciprocal of this number and reducing them to the smallest 3 integers having the same ratio. Eventually, you would come with some kind of an orientation used with these indices known as Miller indices. Okay. Miller indices of some important planes are shown here. These primitive basis vectors, your A, B and C. Okay. So, let us consider this arrangement. So, you will have a vector A here, A here. Okay. So, you can also have A, B and C on 3 different axes. Okay. These describe a crystalline solid such that the crystal structure remains invariant under translation. So, if you have one plane and then you translate that in 3 dimension, you are going to get the same crystal structure. Okay. And this vector which is quantifying this translation is the sum of integral multiples of these basis vectors. Okay. And the direct lattice vector is described as R given by M A plus N B plus P C, which is these are nothing but the intercepts on these 3 different axes. Now, how these planes are oriented, this also affects the eventual IV characteristics of the semiconductor device. Okay. A reciprocal lattice, which we very widely use for studying the crystal structure, and in the subsequent lectures you are going to see that in the reciprocal lattice you actually do your mathematical analysis also to study things like energy bands and all. So, the reciprocal lattice is what which is described for a given set of direct basis vectors. These are defined as A star, B star and C star, okay, and the equations are given here. So, your basis vectors A, B and C are used for obtaining the reciprocal lattices. Okay. So, B by C divided by A dot B by C complement, that is one basis vector in the reciprocal lattice, followed by B star and C star. The general reciprocal lattice vector G is given by H dot A star plus K dot B star plus L dot C star, such that A dot A star is equal to 2 pi, A dot B star is equal to 0 and so on. So, when you multiply the direct basis vector with its own reciprocal, you get 2 pi. If you multiply with another one, you get 0. Okay. H, K, L are nothing but some integers. The direct and reciprocal lattices are related as G dot R equal to 2 pi into integer, any integral value. The volume of a primitive unit cell of the reciprocal lattice is inversely proportional to that of the direct lattice. Okay. So, the volume of any primitive unit cell in the reciprocal lattice V c bar is 2 pi cube by V c. Okay. So, it is inversely proportional to whatever volume is occupied in the general lattice structure, the volume occupied in the reciprocal lattice structure, they are inversely related. Okay. So, the reciprocal lattice is useful to visualize what is known as the EK relationship. Okay. So, now we are basically proceeding towards the material level or the material level analysis of a semiconductor device. Let us see what is an EK relationship. Here E stands for energy and K is a quantum parameter known as wave number, or in some cases it is also known as wave vector, such that K is defined as 2 pi by lambda. So, now if we just slightly take a small detour and discuss about the quantum nature of electrons, it is established and you may have studied in some earlier courses that electron has a dual nature. It can definitely act like a wave, it can also act like a it can definitely act like a particle, but it can also act like a wave, okay, which is provided by the de Broglie's analysis, where we consider matter acting in the form of a wave, these so called matter waves, okay, such that these matter waves have a wavelength lambda and a momentum p. The wave number k is defined as 2 pi by lambda, okay, and lambda can be written as h by p where p is momentum. Okay. So, k is basically directly proportional to your momentum of an electron. The EK relationship which we are discussing here basically is a graph between energy and momentum of an electron. Okay. These vectors or if you consider k as a wave vector, these are mapped into the reciprocal lattice. The primitive cell of a reciprocal lattice can be represented by what is known as Wigner side cell. Okay. So, if diamond lattice structure was in the general lattice arrangement, we saw the diamond lattice structure. In the reciprocal lattice environment, the standard structure is known as Wigner sides cell structure. It is constructed by drawing perpendicular bisector planes in the reciprocal lattice from the chosen center to the nearest equivalent reciprocal lattice site. Okay. This cell is the reciprocal lattice, is also known as the first Brillouin zone. Okay. So, now we are basically moving towards the band structures also. So, with this we would come towards the end of today's lecture. The main aim of this lecture has been to introduce you to semiconductor devices and to tell you why semiconductor devices have become so important and so significant over the past many years. All the gadgets which you use, basically these gadgets have some kind of a semiconducting material or device at its heart of operation. Okay. The semiconductor material, okay, I am talking about the material, not the device itself. Okay. The material or the device is composed of the material only. That material is perfectly crystalline in nature. Okay. That crystal structure we have tried to analyze. Every crystal structure has a repeatable unit known as the primitive unit cell. So, if you analyze one unit cell, you can analyze all the properties of the semiconducting material. Okay. The crystal structure can be described either in the general lattice structure or also in the reciprocal lattice structure. Okay. These are interrelated, they are inversely proportional to each other. In the general lattice structure, most of the semiconductors have a diamond lattice arrangement. In the reciprocal lattice structure, most of the semiconductor can be visualized by the Wigner side cell. The construction of that is explained on your slide right now. Basically, we are interested in studying how these electrons move inside these lattice structure. For that, we need to know its energy, we need to know its momentum. The momentum is explained by what is known as k, either the wave number or wave vector, which is defined as 2 pi by lambda. And using de Broglie's relation, we can say that k is basically a measure of the momentum of an electron. So, for a particular momentum, how much energy your electron has in the crystal structure, that basically plays a very important role on how that semiconductor material is going to behave when used inside a device. Okay. So, in the subsequent lectures, we are going to study this material level properties in more detail. Okay. So, with that we end today's lecture. Thank you.